Hey there, today I want to talk about named entity recognition model evaluation. In my opinion, it's a messy subject. I'm not claiming to know every single way of doing this. I'm just going to share the two approaches that I have used in the past and that are also used in open source software, namely token level evaluation and entity level evaluation. And then we are going to implement entity level evaluation from scratch. Before we do any coding, let me try to explain the basic ideas. What you can see on the screen is a sketch. We have a ground truth piece of text sentence, and the sentence goes like this: Tom Cruise is great, right? And the ground truth entity is Tom Cruise, which spans across two tokens, and its entity type is person. Pretty straightforward. And let's imagine we have some kind of a model, right, that made a prediction. Here I have a couple of examples, but one example that I did not even, let's say, sketch is the case where the ground truth is equal to the prediction. I guess that one is trivial. However, let's look at the mispredictions, right? So one possible misprediction is that we don't predict any entities whatsoever. Then misprediction, let's say 2 and 3, are that we have some kind of an overlap with the ground truth span. However, it's either a subset or a superset of the ground truth. But at least we get the E-type or entity type right. Then we have another possible prediction, number 4, where we get the span right. However, we don't get the entity type correctly. And then another possibility, prediction 5, is that the span of the prediction and the span of the ground truth are not overlapping at all. And finally, we have prediction 6, where the overlap exists. However, it's a different way of overlapping. Why am I showing you this sketch? Well, before you choose the metric family, let's say, you need to answer the question that we have here in red. Are all of the mispredictions equally bad? Let's say that in your use case, every single prediction from 1 all the way to prediction 6 are considered equally bad, and you don't want the model to get any points for them, right? In that case, you would probably want to go for this entity-based approach that I will talk about later. However, if you want to reward the models for at least having some overlap with the ground truth, you might want to go for token level metrics. And before I jump into explaining what these two approaches are, let me first show you one possible way how one can represent named entity recognition pieces of text, right? So we have this IOB notation, which stands for inside, outside, and beginning, and it's pretty straightforward. So let's say this is our piece of text, and we have a single token entity, and the way we represent this is with a list of strings where each entry corresponds to one token, and we see that the first token is the beginning of a person, right? Then let's take the Tom Cruise is great piece of text that we already saw, and here, since the entity spans across two tokens, we say that the first token is beginning of a person, but then we are inside of a person, right? It's still the same entity, and the remaining two tokens are not entities, so we just say outside. Another case is that we have two single token entities, right? But they have different entity types. And even though they are right next to each other, we want to make sure that we always start them with B, beginning, because they are completely independent. And finally, potentially the trickiest example is when we have two entities that are of the same entity type but are unrelated, right? We use the B, beginning prefix to kind of say, hey, yes, both of these, let's say, entities are of entity type location, however, they are independent. So yeah, this is the notation we're going to be using. And now we're ready to finally talk about the two approaches. So let's imagine we have this ground truth. The sentence goes like this: Alex is going to Los Angeles in California. And these are the ground truth entities: Alex, Los Angeles, and California. So person, location. The prediction, it's not perfect, unfortunately. And here we're predicting Alex as a person. Then we take the token going and we think that it's a date. And finally, we put the last 4 tokens together and we believe that it's a location. How do we evaluate this single sample? Well, as I mentioned, there are two approaches. Let's start with the token level, which is arguably the simpler one. And what do we do in this approach is that we look at the entire problem token by token, right? So this approach assumes that the tokenization of the ground truth and the tokenization of the prediction are identical. And if that's the case, right, you can literally have here each row that represents one token. And for each of the tokens, you can basically look at the ground truth and the prediction. Ground truth and the prediction. Maybe you recognize this kind of a table. It's nothing else than a standard classification data set for which you can simply compute things like accuracy, precision, recall, and let's say other confusion matrix derived metrics. And this approach, right, it is going to be a little bit more lenient because even, let's say, if here we mispredicted the two ground truth entities, there's still definitely an overlap, right? So as you can see here and here, these samples are overlapping. Here there's a mistake and here there's a mistake, but we still get extra points for these two tokens. Cool. So that's the token level approach. The entity level approach works in the following way. What do we do? First of all, is we take all the entities in the ground truth. So we have Alex, Los Angeles, and California, right? Alex, Los Angeles, California. Then we do the same thing for the prediction. We take Alex, going, Los Angeles, and California, and we add it to the table. However, we drop duplicates, right? So Alex, we don't want to have it there twice. We kind of drop the duplicate, and we end up with with 5 different entities, 3 of them coming from the ground truth and 3 of them coming from the prediction, and we remove the duplicate. And for each of them, we again just note what the E-type is. And if you look at this table, we can use the same strategy as we used for the token level approach, right? This can be seen as a classification problem where we have Y true and Y pred. And we can simply compute any classification metric whatsoever. And as you would imagine, this approach, this entity level approach, is a little bit more strict, and it would not give us extra points for partial overlaps. So going back to the initial example and this question we try to answer, if you use token level evaluation, you don't see all the mistakes in the same way. However, if you use entity level evaluation, no matter what mistake you make, they are considered equally bad. Cool. So that's the quick introduction. I hope it was clear. And now let me just quickly show you how these are used in open source software, right? A popular library nowadays is Hugging Face Evaluate. And if we look for this keyword seqeval, we open this module. Hugging Face Evaluate is actually calling this third-party library seqeval that implements all of the logic. And what it does, we basically give it the ground truth, right? We give it the predictions. Let's say in the IOB format here, they support way more, let's say, notations, but we don't care. And then we get some kind of a report and we do some renaming and so on and so on. But my point is that we basically outsource everything to seqeval. We'll talk about seqeval a little bit later, but let's try to run evaluate from Hugging Face. So I have a terminal open. Yeah, let me install all the relevant things. So let me get Python and let me create a virtual environment. Yeah, and let's activate it everywhere. Pretty cool. And let me install these two, let's say, libraries that we just discussed. So pip install seqeval and evaluate. So now that we have it, let's try to just write a minimal script that calls evaluate, right? And see what scores it gives to our misprediction. So let's call this a try.py and let's import some stuff. So let's import prettyprint, let's import evaluate, and here we load a metric object, and as you can see, we're outsourcing everything to seqeval. Yeah, let's create our ground truth annotations, and let's not forget we are dealing with our original sentence, which is Tom Cruise is great, right? So the ground truth, as you probably remember, was let's say beginning of a person, then it was inside of a person, and then we had outside and outside. Pretty simple. And first of all, let's just say that the prediction is exactly equal to the ground truth, and let's see what result we get. So we call metric compute, and we say reference is equal. We need to introduce this extra dimension, don't worry about it. And predictions, I believe. Actually, this should be references, predictions, and let's do anodes. Let's say, what is it? Prediction. And this, in my opinion, should give us what we want. So let's do pretty print result, because it's going to be a dictionary. That's why I decided to pretty print. And let's do Python try. We have a bunch of, let's say, keys, but all of them basically evaluate to 1, right? So this is something we would expect. But let's go and comment out the previous prediction, and instead let's assume that we basically predicted nothing, right? So yeah, let's run the same thing again. And as you can see, there are like a bunch of metrics that evaluate to 0, meaning that this was considered as basically a no. However, there's a single metric here that is equal to 0.5, right? And I looked into the source code of, let's say, seqeval, and basically this is the only metric that is using the token level evaluation, because as you can see here, if we go token by token, right, we got this token wrong, we got this second token wrong. However, the two outsides at the end, we got them correctly. And if you were to create the same table we created here, right, you'd basically have 4 samples, and the accuracy there would be 50%. So yeah, and if we go to the source code, it's exactly actually well, or it should become obvious. So for all the scores except for the overall accuracies, evaluate is using classification report from seqeval. However, for the accuracy, they're using accuracy score. So this is token based, but this is or let's say token level, and this is entity level. And yeah, just to kind of prove to you, these two are imported from seqeval. And yeah, while we're here, let's go to seqeval really quickly, and let's try to look at the implementation of this accuracy score. And I mean, I think this code is pretty self-explanatory. We just unpack the lists again. For some reason, they always assume that you have multiple documents, whatever. But once you have the ground truth and the predictions, you just count up the number of tokens where the label agrees, right? And you divide it by the length. So this is just a standard token level accuracy. Let's try some other mispredictions, right? Let's see what happens if we predict the prediction 2. So if we do something like this, and we just say, hey, we only get the Tom part, right? Let's see. And again, we're expecting all the metrics to be 0, because except for this number, which is, let's say, a support, because they are entity level. However, this accuracy, again, it's token level, so that's why it's 75%. And yeah, let's also try, let's say, prediction 4, right? You can try all of them, but my point is that they will always be 0 for the entity level. So let's say we thought this was a location, right? And here we set inside of a location, and let's see. And as you can see, we basically get zeros everywhere, but the accuracy is again 0.5 because the last two tokens agree. Cool. So that's more or less it for the explanation part and what is going on inside of relevant open source libraries. But if you're interested, what I'm going to do for the rest of the video is trying to implement this token level evaluation here from scratch. There's nothing tricky about it. Yeah, I just thought it might be a nice exercise to do it from scratch. But in real life, you would just call seqeval or evaluate from Hugging Face. I actually wrote unit tests already so that we spend a little bit less time on implementing things. So there is a file already that I call test hours. And it assumes that we implement these 4, let's say, functions. And yeah, we just want to make sure that all of these tests are passing. But to quickly tell you what we will implement, we will first of all check whether a sequence of tokens in the IOB2 notation is valid, right? So that's this check valid function. Then get entities. This get entities function will, for each, let's say, list of strings, it will try to extract the entities to be able to that are basically represented as rows in this table. And get e-types, this will be a helper function that only looks at the actual e-type. We don't care about the IOP, let's say. And finally, get report will give us the full classification report of the entity-based evaluation. And that one is basically similar or identical to what seqeval is giving us. Cool. So let's get started. First of all, let's implement the check valid function. So we create a file called hours. Just to make sure that these tests are not yelling at us all the time, let's just create stub functions for everything that we want to implement. Definition of check valid, right? And let's do pass. And let's do this also for the get entities. Let's also do this for get e-types. And finally, let's do this for our get report. Cool. And yeah, let's get some imports. We'll use regular expressions, import pandas as PD. We will use pandas to do this merging with dropping duplicates. And finally, we import scikit-learn, import the classification report, because again, I'm repeating myself, but eventually, once we create the table, this is nothing else than a standard classification prediction table with y true and y pred. So first of all, given a list of strings, we want to make sure that it's a valid IOB2 sequence. What do I mean by this? So if it's, let's say, a simple empty list, it's valid, right? However, if you have an invalid token like here nonsense, we want this function to give us false. Let's say 3 outside tokens, this is correct. Here, the reason why this is not correct, right, is that we cannot start with an I. The entity always needs to start with a B. And similar, let's say, point here, we started B organization, however, then we had I person, which is impossible. So we just want to make sure that our evaluation does not allow for inputs like this that are malformed, right? Well, it can happen if you have a prediction model that kind of does not enforce this, like whatever, some kind of a like conditional random field. You might need to do some post-processing so that these are satisfied, but that's not the topic of this video. Anyway, cool. So check valid. So it accepts let's say annotation. So annotates is a list of strings, and what it will return is a boolean. And first of all, let us define a pattern with regular expressions that represents what we are allowed to have inside of a single token. So allowed pattern, right, is something like recompile. We have 3 options. Either we start with an O, right, and right away we end that string that would correspond to the outside, right? Or there's another possibility, and that is that we start with a B and then there's a dash, and then there is some number of characters representing the entity type. Maybe this should be actually plus, right, if I'm not mistaken. It can be any character, but occurring at least once. Let's actually add a test for this. So we don't want to allow for this to happen. So let's say this will be false. Finally, we can also, let's say, be inside, right? And the same logic here. And so that's the allowed pattern, right? However, we continue here. For convenience reasons, let's just prepend our annotations with an outside token, right? So that we don't have to have a lot of if statements handling whether we're at the beginning or not. Also, let's save the length of the annotations. And here, first of all, let's make sure that every single token in our sequence matches this regular expression. So if any allowed pattern match annotate is none for annotate in annotates, we just return false. So this should be a short circuit way of doing this. So we iterate through every token, right? And we just try to match our regular expression. And if we don't match it, it will return a none. In that case, we right away return false. Cool. If we pass this condition, we're not done, right? Because let's say this condition would be enough to determine that this is false, right? And this is false. However, this condition would not be enough to prevent, or let's say this I dash or inside tokens to be the start token. So let's handle this one, and I think then we should be done. So what do? We just iterate through every, let's say, single pair, right? So for e in range 1 all the way to n. And what do? We look at the current annotation, or let's say the current token, and we kind of look whether it starts with an I dash. So if annotate starts with I dash, right, we need to do some checking here. If the previous one is outside, or what is the second condition? So basically here, this condition itself, it would catch, let's say, this case, right? If there's an O before an I, it's a false. However, it would not catch this, let's say, illegal sequence, because before an I, there was a B, which would seem legal. However, the entity type was different. So let's make sure that if there's an I, then the previous token's entity or entity type is identical. So we just say, hey, I want the previous token's entity type to be, let's say, identical. So here we're doing the opposite, right? So in case they are not identical, or in case it's an O, we return. However, if these two things are, let's say, satisfied, we just return true, because our checks pass, right? And let me test it out. Let's maybe focus on one specific test. So test check valid, and of course I need to get by test. So let's see by test, and we only run our test that we see on the right, and it passed, which is nice. Let's just try to break it, making sure that it really works. So let's say there's an I here. Okay, cool. So I think we implemented this correctly. Let us now move to the other function, which is get entities, right? And actually, I apologize. This one is called get etypes. So let's maybe start with the get etypes here. And sorry for the ambiguous terminology. Etypes are just the thing to the right of our string, right? Organization. Whenever we stumble upon an outside token, we just return a none. However, when we stumble upon a beginning of something, we just return the thing that's to the right. So we give it a list of strings, right? Annotates, exactly. And what we want to return is a list of either none or string. And what we can do this in a one-liner. Let's just basically iterate through every single token and get everything starting from the third character, right? Only if the token is not equal to 0, else none for annotate in annotates. Let's make sure that it works. So we do test get etypes. Cool. Now let's get to the, let's say, trickier one, probably the trickiest part of this video, and that is the get entities function. So what does it do? We give it a sequence of tokens, right? But what we want in return is a list of entities, and each entity will be represented as dictionary, right? So here, for example, we have a single token entity that starts at token 1, ends at token 1, inclusive, right? It has an e-type of org. Here, another example is that we have two entities, right? Because they are both B, but they have the same entity type. Then, for example, here, yeah, exactly here, we have a single entity, but it spans two tokens. We say start and end, and it's a person. You get the idea, right? We basically completely destroy the token level structure, and we only collect the actual entities. Let's get started. I can finally use some of the functions that we have implemented before. If somebody provided us with an invalid list of tokens, we right away raise an exception or something like this, right? So let's do this. If not, check valid our anodes, and of course let's do anodes list of strings again, and this is going to be list of dictionaries with key strings, and the values will be either integer or string, right? So we check whether the input annotations are valid, and if not, we just raise a value error, and let's say invalid input. Nice. And if it's valid, let's actually think about how we're going to do this. Similar to what we did before, let's prepend our annotations with an outside token, and also let's append the annotations with an outside token. And anyway, start pattern is going to be a set of all possible pairs that correspond to ways how an entity could start, right? So let me maybe write it down, then I will explain. So first possible starting pair is that the previous token was outside and the current one is B dash, right? That's probably the most normal pattern out there. And let's say this would correspond to something like O and B location. Pretty straightforward, right? Then another way how an entity could start is by having a pair of two beginnings, right? And a specific example could be, let's say, beginning of a person and then beginning of some other entity type, like location. The third possible way is by having this pair, right? And as you would imagine, let's say this can be B location. Then we have a continuation of a location. However, the last one is going to be a person, right? So we have all possible start patterns. Now we just need to do the same thing, but for the ending patterns, right? So if I do end, and here, let's maybe completely delete what we had, and let's enumerate them all. So the first of them is going to be this one. I think this one is straightforward, right? Like we can just say, let's say B location, something like this. Let's say continuation of a location, and finally we would have an O. Cool. Let's continue. Let's do B and O, and this one, I mean, we can just do something like this, right? Again, this is a single token, let's say entity. And we have two other options, surprisingly, or not surprisingly. Here, we can also write the same thing as we wrote in the start patterns, because if I use the same example, actually, paste it here, this was a starting token of the entity person. However, at the same time, it was the ending token of the entity person. And finally, we add I and B. It's also a starting pattern, because if an I is followed by a B, it means that this was the ending token of the previous entity. Entities. So let's prepare the list of all the entities we will detect, and let's type annotate this. We already have it in the function signature. So dictionary, sorry, string, integer, or a string. Cool. And at the beginning, it's going to be an empty list. And let's just run the algorithm, right? It's going to be similar to what we did before. We will just iterate through every single pair. We will detect the starting pattern and the ending pattern. And whenever we are inside of an entity, right, and we hit the ending pattern, we just add it to our list of entities. And we also use this variable start to represent whether we are inside of an entity or not. While I is smaller than n, we get the two annotations and annotates I. Let's create a pattern. Previous. This is the pair of consecutive tokens. If the pattern is in n patterns, and at the same time we are inside of an entity, we want to cut it off there, right? And we want to add it to our list. So entities append, and we add the start, which is start -1. Note that everything is shifted by 1. And since here the end is not inclusive, we need to, let's say, take I and subtract 2. And finally, the e-type is something we simply get from the current annotation. Finally, since we create a new entity, we just set start to none, which means that we are ready to enter a new entity, right? And here we have a if statement checking whether we are matching a start pattern. If we are, we just say start equal to I, and yeah, we increment our I. And finally, it should return entities. And I think we should be done here. Let's check that our unit tests are working. So this is not working because we forgot to get the n, which is, as in the previous functions, the number of annotations, so length of annotations. Let's see. And defined n patterns. Yeah, both of these are actually plural, right? These list of patterns. And start pattern is not defined. Start pattern, yeah, something like this. Let's hope it works. Whew. E-types. Yeah, because we also want to use here our, let's say, other helper function, which is the e-types, right? And get e-types annotates, something like this. Get e-types. If I did not misspell it, it would be great. Yeah, so it worked. Yeah, as you would imagine, now we are almost ready because we are at a point where we made it possible to take any, let's say, list of tokens, right, and extract the actual entities, no matter how many tokens they span, right? And as you would imagine, now the only thing left is that we will run the function get entities on our ground truth. We will run it on our prediction, and we just collect them using pandas in this nice table, making sure we drop duplicates. So in a way, it will be, let's say, a merge of two tables. So let's give it a try. We have this function get report, and this function get report, it should input two different things, the true ground truth annotations and the predicted annotations. Let's do annotates true is list of strings. Let's do annotates pred is again the same thing, and finally we will return a dictionary. I'm not going to add the types because it's nested and so on. But before you implement this, how does the unit test work? So here you have the unit test. We always, let's say, give it two list of strings. One is the ground truth, the other one is the prediction, right? And what we want inside of the unit test is when we run our function and run the seqeval function, that except for like a couple of keys, there are small differences, right? We want to make sure that our report is the same as what seqeval gives us. First of all, what we want to do, right, is to make sure that they have the equal length. So length annotates true is not the same as the length of predictions. We raise value error, and we just say unequal lengths, right? Let us now use our getEntities functions. I can do the following: entities true is equal to pd data frame, and get entities and it's true, and here predictions get entities prediction. Just rename the columns, because right now, if I'm not mistaken, like we can actually put a breakpoint here just to kind of show you what's going to happen. So let's do test get report, and entities true looks something like this. Yeah, it's a single entity, whereas empathy prediction, it's the same thing, right? So here we have a perfect match. But my point is that the columns are start and end, and the e-type, and we just want to, for convenience, rename in the, let's say, for the ground truth entities, to name this to e-type true, and for this one, rename it to e-type predicted, because we want to merge these two tables and keep the both of the e-types in there. Entities true rename, and we say, hey, please rename the columns with the following mapping. E-type is going to be mapped to e-type true. And we do the same thing for the truth, or for the prediction rather. So prediction and find true prediction, right? So if I were to put the breakpoint here now, and we run this, pytest entities predicted, or let's say true, same type as before, and entities predicted, now they have a different name. And at this point, right, what we can do, we can just merge the two tables. We can just say, hey, take the true table and merge it with the predicted entities predicted. And we want to make sure that, again, we drop duplicates. So we want to do, let's say, an outer join or merge. And we need to specify on what two columns to merge, because there can be, let's say, multiple occurrences of the same e-type. So we want to say, hey, merge on start and merge on end, right? But how do it outer? Which means that, yeah, you drop the duplicates, but if there are entities in the truth that are not in the prediction, keep them, and also vice versa. So if we try this here, since we literally have the perfect prediction, there will be just one row, right? Let me put this piece of code that we just wrote into the source code. Let's say df merge is equal to this one. What we want to do is to also make sure that we fill some missing information. Let me maybe show this to you on a better example. As you can see here, there was no location in the prediction. So here, the ground truth has both person and location. However, the prediction only has person. And after merging, right, the default behavior of outer is that it will populate it with none. So we just want to make sure that we populate this with an empty string. Let's just do this, fill NA with something like this. And let me actually go there. Let's look at our df, and let's look at our df for this one. Yeah, this is how it looks like. Let's maybe continue our df. Here it's like perfectly wrong, right? So what else is there? We literally just need to take the e-type true column and the e-type predicted column and send it over to scikit-learn. Report is equal to classification report scikit-learn, and we do df e-type true. We do here e-type predicted. We do output dictionary equal to true, because we want to have a Python dictionary rather than printing things to the standard output. And also here, let's also provide all the possible labels that one can have, right? And in our case, it will be all the entity types in the ground truth, union with all the entity or unique entity types in the prediction. So here we have person, location, person, date, and location. So all possible labels will be these three, right? So we just want to give this to scikit-learn. So we do labels is nothing else than a set df e-type true, right? We cast it to list, and we do the same thing with the set of df e-type prediction to list here. This is like one big set after union. However, we just want to subtract the outside label from it. And I think this should work. Yeah, here we cast it back to list. I think this should work. And finally, what we do is to like return our report. All right, let's see. PyTest. Yeah, actually, I see the problem. We actually want to here exclude the empty string. If I go back to what we did, if we always go, let's say, here somewhere and run our unit tests, the only thing that the df contains are the, let's say, entity types and then an empty string, right? But we don't want to run the analysis for an empty string. Or let's say the classification report for the empty string. So let's see, PyTest. This should be good. If we disable the warnings, there are a bunch of divisions by 0. Long story short, I think we are done. Let's run all the tests at once. Yeah, looks pretty good. This is how you can implement it. Yeah, I hope you found this video interesting, and I'll see you next time.